All right, so today we're going to talk about water and the different properties of water that makes it important and essential for life. So let's begin by looking at the structure of a water molecule. So we all know that water is H2O and it's made up of 2 hydrogen and 1 oxygen. Water is said to be a polar molecule, and what that means is that there is an equal share of electrons between oxygen and hydrogen. Now, this oxygen right here is more electronegative, which means the electrons from hydrogen is actually pulled closer towards oxygen. The same thing here. The electron of this hydrogen is actually pulled closer towards oxygen, and that leads to polarity. In chemistry, when you say something is polar, it means that there is a charge difference. So this side of the water molecule is said to be partially negative, and these sides are said to be partially positive. This means partial. Since you have these partial charge difference, it means if I have another water molecule adjacent to this one, if I draw a water molecule, and this is partial negative, partial positive, partial positive, these two molecules are attracted, and the attraction is called a hydrogen bond. So a hydrogen bond is actually formed between this partially positive side of one water molecule to the partially negative side of the adjacent water molecule. So let me draw a hydrogen bond by using this line. So you have here a hydrogen bond between two water molecules. Now this hydrogen bond between your two water molecules and the polarity, or let me just put here dipolarity, two different charges of your water molecule, gives water its different properties. The properties of water that you need to learn are, first, cohesive property or cohesion. Next, you have adhesive property or adhesion, and you have thermal properties, and lastly we have I'll just put it right here, solvent properties. Alright, so for cohesion, it is said that water can actually stick to other water molecules. So I'll put here water to water to water to water. So all of those individual water molecules can stick to each other. And an example here is the movement of water in a plant. If water leaves through the leaves, and if you think about it, how can water from this ground or from this soil, how is it able to go up the stem into the branches and into the leaves? The reason is cohesion, because water pulls each other, like stick to each other, and when one evaporates, one water molecule evaporates, the rest are pulled up. So water can stick to each other. So this is what we did in class earlier. I asked you, how many drops of water do you think would be able to fit in the surface of a small coin? And we kept dropping, and we actually reached about more than 80 drops. And that dome of water is still not breaking. And how is this possible? Because imagine all the individual water molecules in this area are sticking to each other. So they're holding themselves together, and that property again is called cohesion. Okay, so the second property of water that we need to know is the adhesion. And adhesion is kind of the same as cohesion, but adhesion makes sure that you understand it's water sticking to surfaces or any kind of surface. Let me show you this picture. So what this picture is showing is that, for example, you put water in the first cup and you put tissue in between those paper cups. The water right here can actually move from this plastic cup to the next plastic cup. You can try it out as well. If you have a puddle of water, you put tissue, water can actually seem to like crawl up the tissue paper, and that property is called adhesion. It can stick to surfaces. Alright, so the next property is thermal property. I wrote this down already, and there's three things we need to know. First, that water has a high heat capacity, or water has a high specific heat. That's a measurement in chemistry that tells us that it takes large amounts of heat. Water can absorb large amounts of heat, and these are all correlated, by the way. Water has high latent heat of vaporization. It needs large amounts of energy before it evaporates. And the third one is high boiling point. Again, water needs a large amount of energy before it can change from liquid into gas. Alright, so what is the relevance of all of these property to, let's say, us in our body? Now, we talked about how your sweat contains water, and since water has a high specific heat, it has a high latent heat of vaporization, and it has a high boiling point. When this sweat leaves the surface of your skin, it actually has a cooling effect, because that amount of sweat that evaporated carried with it a large amount of heat as it evaporated. So if you're sweating right after an intense physical activity, that's good, because your body is actually trying to produce sweat to cool you off, since muscular activity generates large amounts of heat. And the last property we need to be familiar with is the solvent property. Although this is actually the most popular property of water that you might have remembered from middle and lower school. And you always say water is a universal solvent, which basically means it can dissolve many things. Now, we have to know that not everything dissolves in water, though. If a molecule is hydrophilic, then yes, it can dissolve in water. But hydrophobic molecules, such as many organic solvents, actually cannot mix or dissolve in water. So these hydrophobic molecules are nonpolar molecules, such as fats, oils. Okay, so they don't readily mix with water. Let me show you quickly. I have this in my table. Think about it. Which one is oil? Which one is water? So you can see the green is not mixing with the white, and the green is settling down. Which layer is water? Which layer is oil? Okay, so what is the relevance of water solvent property in our body? So we need to look at the blood. Our blood is mainly water. The plasma is made up of water. And how do we carry and transport different types of nutrients in our blood? So let's look at, I'll just put a box right here. So first of all, salt. So salt is a polar molecule. It's charged. Therefore, it can readily dissolve in water. Let's look at another one. Glucose. Glucose is also a polar molecule, and it can be readily dissolved and transported, circulated in the blood. What else? Now, oxygen. Oxygen is a nonpolar molecule. There's equal sharing of electrons in oxygen. So how is oxygen transported in the blood? Oxygen is nonpolar. However, it's really, really small, so it can actually dissolve in water. The problem is, as the temperature increases, the solubility of oxygen decreases, and our body temperature is about 37 degrees. That's warm, and this prevents oxygen from becoming fully dissolved. Therefore, the body has a different mechanism of carrying and transporting oxygen, and this is actually transported in your red blood cells. So your red blood cells contain hemoglobin molecules that are able to attach and detach oxygen. So that's how oxygen is circulated in the blood. I'll put there AA, that stands for amino acids. You already drew the structure of amino acid, and you should know that amino and the carboxyl group gives your amino acid an overall polarity, an overall charge. Therefore, again, polar can easily dissolve and be transported, circulated in the blood. Now, how about fats and cholesterol? I've mentioned earlier cholesterol. They are non-polar molecules, therefore they're not readily dissolved in the blood. So how are we transporting this in our blood? So remember this new word, chylomicrons, or lipoproteins. Let me show you that picture. As you can see here, the cholesterol or your fat molecules will aggregate and stick to each other, and they will be surrounded by phospholipids and protein molecules. Now, phospholipid and protein molecules are charged. So once they're packed into these circles of lipoproteins, then they can now be transported in the blood. And if it reaches areas or cells that need these lipid molecules, then it will be deposited in, for example, your adipose tissues. So before it reaches your adipose tissues, it will be packed as a lipoprotein and then circulated in the blood. So let's go back to our concept map. So these are the different nutrients that is transported, dissolved in blood, which is basically water. Okay, let's see, what else do we need to know for this unit? Now, all of this property of water makes it very unique and ideal and very useful for living organisms. Now, you need to actually also know how water, which has about 18 grams, is different chemically with methane, CH4, that's methane. And methane is about 4 plus 12, 16 grams. So if you look at the molar mass of methane and water, it's similar in mass. However, you will wonder, water is liquid in room temperature, but methane is gas in room temperature. Now, how is one gas, or how is one liquid, even if they have almost the same molecular weight? Now, let me show you a table to quickly differentiate between methane and water. Okay, so make sure for the test you can discuss at least 2 or 3 differences between methane and water. So water, even if they're the same molecular mass as your methane, shows us different useful functions: solvent, thermal properties, cohesion, adhesion.